Hello, today I'm going to talk about the Shale Basin Analysis Project, creating and using simulations to explore the geologic past and present of the Central Mackenzie Valley, Northwest Territories. So for a bit of background, the Central Mackenzie Valley, in particular the Mackenzie Plain Exploration Region, currently is, and has been for many years, the main focus of research for many organizations, including our own. This research is mainly concerned with the Devonian-aged rocks and, to a lesser extent, the Cretaceous. So this current NTGS project, the Shale Basin Evolution in the Northwest Territories, began in 2015, and my study is part of a sub-project of the greater Shale Basin Evolution project. So the area of interest for basin analysis encompasses the Mackenzie Plain Exploration Region over here, and adjacent portions of the Peel Plain, Peel Plateau, Mackenzie Mountains, and Franklin Mountains. The project's main focus is the Gavetian-Dufresnian Age Horn River Group, which includes the Hara Indian, the Ramparts, and the Cannel formations. This group is also known to include two intervals with hydrocarbon potential, the Bluefish member of the Hara Indian Formation, and the Cannel Formation, which is the source rock for the oil extracted at Norman Wells. The Keyscart member of the Ramparts Formation is the reservoir for that field. So, what is basin modeling good for? First of all, it's an important tool for understanding basin evolution with time. While it is a simulation, the model uses real-world data as its principal source of input and for calibration. Once the model is complete, one potential use for it is to help predict the economic potential of an area. So the software that I'm using for this project is called Zetaware. It has three modules that are all integrated with each other. The first is Trinity, a map-based petroleum systems analysis tool. It can integrate geologic history with hydrocarbon generation and migration. You can also generate 2D paleo cross-sections and play them back to see how the basin developed through geologic time. You can see some of the outputs in the pictures to the left. There's also Genesis, which is what they call a 1D modeling tool, but here I'm going to call point models. It can be used for temperature, pressure, or maturity modeling. Kinex, which is used to model source rock maturation. It predicts the composition of expelled hydrocarbons and properties such as gas-to-oil ratio, vitrinite reflectance, and fluid density. So to begin with, there are approximately 600 wells and 30 outcrops in the area. My first step was to view the data available for each one and discard wells that overlap others or wells that don't have enough data. These are typically shallower wells or injection wells, most of which are in the Norman Wells area. In the end, I narrowed it down to about 100 wells, typically more recently drilled ones because they tend to have better well logs with full geological reports, so chip sample and core descriptions. I also favored wells with maturity data that was available from sampling actual rock, such as vitrinite reflectance and Tmax. So one of the first steps was to format the data for input. Like the example here from the East McKay I-55 well, at minimum you need location coordinates, surface elevation, here I'm using Kelly bushing, and the rock units with the top depths, approximate age, and proportional lithology by percent. And this would be based on approximation derived from a lithology log or a geological report by the well site geologist or another source. To make our point models, we need more than just the well data. We also need to make a series of assumptions. These aren't just guesses. They're based on best available knowledge. The three most important ones are the timing of unconformities, an estimate of how much rock was removed at these unconformities, and then an estimate of the regional heat flow. This matters a lot, in particular, for maturity versus depth modeling. Since the heat flow is probably the most important, so that maturity modeling is as accurate as possible. This can allow us to refine the first two assumptions, but more on that later. With that said, here are some of the assumptions I've used, based on estimates from other researchers. So I've got some estimates on the thickness of rock removed at 3 unconformities. You can see the main one is the subcretaceous unconformity, and that the amount of missing section can vary by quite a bit throughout the study area. I also have an estimate of the average regional heat flow from an older publication here. To build our point model requires programming the stratigraphic column in reverse, from top to bottom, or youngest unit to oldest. It's a bit unintuitive at first, but once I figured out that the software allows you to enter unconformities after entering the existing rock units, things became a bit quicker, and the amount of cryptic error messages decreased. Now I'll show a few examples of point models that I've set up in the software so far. All of these have accompanying maturity data and therefore can have their simulated maturity curve calibrated to reality. These 4 examples I'll show, so the Cranswick A22, Bluefish K71, Keel South A28, and Dahadini D65. These are all existing oil and gas wells, and these 4 examples will form a bit of a northwest to southeast transect through the study area. So this is what the models look like in the Genesis module. As you can see, there's a great deal of variation in thickness in our interval of interest here. So the Horn River group is right here between the Imperial and the Hume. So it's much thinner in the northwest, and kind of a medium thickness through the middle of the basin, and once you get to the southern end, the package thickens quite a bit. Now this is very generalized. There's a lot of variation throughout the basin, but I'm limiting the amount of examples I'm showing here. And the other thing that varies quite a bit is the amount of Cretaceous or more recent rocky strata overlying the Devonian Imperial Formation. So your subcretaceous unconformity would be this bluish line here. Here. With maturity data from sampling, in this case vitrinite reflectance, we can run the point models and generate a simulated depth versus maturity profile. Most of the time, the first run of the model won't line up well with the data from chip samples. In that case, we usually have to adjust unconformities and missing section. Sometimes, an unconformity has to be added. Let's look at some examples. If we look at A22, here's the subcretaceous unconformity and a period of more recent erosion I added to help fit the data a little bit better. And that makes it fit reasonably well with the chip sample vitrinite results. So we'll call that a reasonable correlation. For the Bluefish K71 well, the lower part of this maturity curve seems to match what vitrinite reflectance data we have. So this is a pretty good correlation here. However, there's a bit of a disconnect above the subcretaceous unconformity down here. So this implies potentially that there is some more recent either late Cretaceous or post-Cretaceous erosion that I didn't factor in. that would pull this curve more to the right, and might also imply, so if pull this curve to the right would imply that the amount of erosion along the subcretaceous unconformity is actually lower than what I've input. So probably more correlation or calibration needed on this particular model. In these last two examples, look at Keel South A28, correlation seems pretty reasonable. However, this one has already been calibrated, so there was a period of erosion added just post-Cretaceous in the model that seemed to help fit the Cretaceous maturity much better, and the lower maturity fits pretty well. So we call that a reasonable correlation. We look at Dahadini D65. There's been some calibration done here. A more recent period of erosion added. It's pretty close. There might be some minor adjustments needed, perhaps adding a bit more erosion of the subcretaceous unconformity to better match reality. This point seems to be perhaps a bit of an outlier, maybe a caving. But overall, this is a reasonable correlation, minus some minor adjustments. There's a few other things you can do with these point models. You can make a series of burial models with different parameters. So first here we have temperature with burial depth for the Keel South A28. Another one you can do is plotting maturity using calculated reflectance according to the curve I showed before. And it shows that our package of interest here, the Horn River group, would have likely gone through the oil window back shortly after the Devonian, and then went well into the dry gas window sometime during the Jurassic. So this isn't too far from the reality. This is a well in the more southern part of the Mackenzie Plain, and the Devonian here tends to have higher maturities than it does in the Norman Wells area. In this burial model, I added a modeled hydrocarbon, or rather kerogen, to the canal formation, and had it go through the maturity modeling, and it estimates that the kerogen would have gone through the oil window sometime during the Permian and Triassic, and then during the Jurassic hit the dry oil window, and would probably, and by the time you get to the present, all of the kerogen in the canal would have been converted to hydrocarbons and then to dry gas, probably. Some of the future work that needs to be done, first of all, the last few point models have to be generated and calibrated to vitrinite reflectance data. Also potentially would look to include some selected outcrops to delineate the extent of some of the rock units a little bit better. Next, I'd need to generate some regional cross-sections through the basin at various orientations, followed by regional mapping of the rock units using some interpreted seismic lines. And lastly, a regional model of hydrocarbon generation, expulsion, and migration will be generated for the Canal and Bluefish shales, to be potentially compared to known accumulations and seeps. Thank you for listening.